We're going to find some maximum and minimum values for this function on the domain that's given. Because it's a closed domain, we know for a fact that the function is going to have a maximum value and a minimum value. What we're going to do is find the critical points using the derivative method, but then also test the values on the boundary of the domain using another derivative method, but it's something that can be reduced to a single variable approach. So number one, we're going to find critical points. Okay, so if we want to find critical points, that means that we want to find the points for which both of the first partials are 0. In order to do that, we need to find the first partials in the first place. So the first partial with respect to x will be 6x squared. The y to the fourth disappears because from x's perspective, that's a constant. Partial y is going to be 4y cubed. Same thing happens to the 2x cubed that happened to the y to the fourth. Under the x condition, it goes away. It's considered constant. Now, think about what it would mean for both of these to be equal to 0. The x1 is only equal to 0 when x is 0. The y1 is only equal to 0 when y is 0. That means that this is, well, actually, hang on, let me rephrase that. Fx and Fy are only both 0 at the origin, at 0, 0 itself. So the first step here, where we go to find the critical points, we locate a critical point. It's the only one for this function. It's at 0, 0. Now, usually we would progress to the second derivative test if we were finding local max and min points. But in this case, we don't care about that because we're finding the absolute max and mins. So we're going to take the 0, 0 and just throw it in the bucket of things we're going to test at the end of the problem. Okay? So I'm going to say points to test over here. It'll be 0, 0 at the beginning. And now I'll get rid of all of this. And now I'm going to worry about the values of this two-variable function on the boundary of the domain. The boundary is the circle x squared plus y squared equals 1. Now, yes, it is phrased as an inequality here. However, that inequality is meant to give the interior of the circle, but also the edge of the circle. When we went looking for critical points, the interior of the circle, that's like when you cover a two-dimensional area, that's when you're looking for critical points to look for any isolated places where the function may take on a max or min value. In a connected domain, it'll only have a chance to achieve a max or min value when it has a critical point. But on the boundary of the domain, that's the closure, the portion that makes it a closed domain. At the boundary of that, that's where we're really interested in checking to see whether it has a max or min value along there. So we're not going to pay attention to the inequality version. We're just going to pay attention to the equation version. And specifically, we're going to solve this for y to get that y equals the positive or negative square root of 1 minus x squared. The reason we're going to do that is that y to the fourth is easy to sub in now to turn it into a single variable function. So then f of x and y equals 2x cubed plus y to the fourth. Well, yeah, but now we can turn it into purely a function of x, 2x to the third plus or minus the square root of 1 minus x squared to the fourth power. See how this is now a single variable function, and this is true along the boundary. Well, let's expand and do all the funny things that are going to happen with this power. So when you raise a positive or negative number to an even power, which is going to happen with that fourth power, now we don't need to worry about whether it was plus or minus because that will go away. The first square removes the square root. So really, this is 1 minus x squared squared. That's what this turns into. And you can expand that square pretty easily. It's 2x cubed from before, and then expand that out. FOIL it quickly. It's going to be 1 minus 2x to the second plus x to the fourth. Okay, and obviously everything is most polite if you write it in standard form, just with descending powers. At this point, you do not want to solve this set equal to 0. What you want to do is take a derivative of this, because this is the single variable function along the boundary. And along this boundary, you can take a derivative with respect to x, just normal old Calc 1 style, and say, where does this reach a max or min value? So f prime of x equals, this is just normal old derivative. It's 4x to the third plus 6x squared minus 4x. Now, this is the thing that we go and hunt for critical points with when we're looking along the boundary, because now we have it reduced to a single variable function. If this equals 0, we're going to factor. First of all, 2 can come out, and so can x. 2x times 2x squared plus, plus 3x minus 2 equals 0, and that can factor. This is 2x times 2x on the first one, x on the second one equals 0. And let's see, I need a minus and I need a plus. And the plus should be a 2 to make that into a 4x. And the minus should be a 1 to make that a minus x, so that I get the plus 3x that I want. So this is the right factorization. This tells me that my solutions are x equals 0 from this factor, x equals a half from this factor, and x equals -2 from this factor. Keep in mind the places that you're actually interested in. Every time that you find one of these points, you have to check and see, is it inside the domain? Well, this domain is a circle with a radius of 1 centered at the origin. Anything outside of that domain has to be rejected. X equals 0, yeah, that exists in this domain. X equals a half, that exists too. X equals -2, no, it doesn't. This is outside the domain. And so although we didn't make a mistake in finding it, it's important to note at this point that it is outside what we're actually interested in. If we were looking at a bigger domain, like x squared plus y squared was less than or equal to, say, 10 or something, then -2 would be in the club. But in this one, it's not. So we're going to add to our points to test. We're going to add 0, comma, and now you need to say, well, wait a minute, what is like 0, comma what? What is this? Look at what 0, comma something is on this domain, on the boundary of the domain, which is this. That's the boundary of this domain. X is equal to 0 here and here. So there are two places that we should be interested in. There's 0, comma +1 and 0, comma -1. See how that works? So now we're also going to look at the 1/2. Well, think about your unit circle. X is equal to 1/2 here and here. There are two places. You're looking at the entire circle, not just half of it. And at those places, if you remember your unit circle, which I'm guessing you do, then y is equal to either √3/2 on the top or -√3/2 on the bottom. So that's plus or minus √3/2. Okay, now we have a complete list of points to test. We got the first one from critical points, and we got the second and third ones, which are really the second, third, fourth, and fifth ones, from this plugging in around the boundary. Now that we have the points to test, we can forget about all this stuff and just go and test these in the actual function. So, final test. We'll do f of 0, 0. That's obviously equal to 0. And again, we're looking at this function, the very, very first original function. So 2 times 0 cubed plus 0 to the fourth, that's 0. So now we've checked this one. Okay, well, let's do f of 0, comma 1. That's 2 times 0 plus 1 to the fourth. That's 1, right? And if you look at f of 0, -1, well, the y is being raised to the 4th power. So actually, the f of 0, -1 is going to be the same as that. Because if you raise -1 to the 4th power, you get the same result as if you raise +1 to the 4th power. So that's going to be 1 as well. So now we've checked those. Now let's check the final options. 1/2, comma, √3/2. Now, hearkening back to what just happened with the y's with the last one, we should know that actually both of these values are going to be the same. Okay, let's go and find out what they are. This one's messier than the last ones. 2 times 1/2 to the 3rd power plus √3/2 to the 4th power. Again, the plus or the minus will have the same value, so I'm not even going to write that. √3/2 to the 4th power is √3/2 squared and then squared again. So I'm going to simplify it like that in this step. This will be 2 times 1/2 to the 3rd power, which is 1/8. And then this will be 3/4 squared. Do you see what happened there? I squared √3/2, but now there's another square left to do. One more step. 2 times 1/8 is 1/4. And 3/4 squared is 9/16. A fourth is 4/16 plus 9/16 is 13/16. So here I have this set of values to test. I've got the 0, I've got a couple of 1s, and then I've also got a couple of 13/16. So the minimum value here is 0, and the maximum value is 1 on this domain. Cool, huh?